of air in the thoracic cavity and reduce it, that makes the pressure increase, and that expels air out of that cavity. There's actually a really cool thing you do with a water bottle. If you take let's say a sports drink water bottle, not one of the thin water bottles, but one of the tougher ones, if you cut it halfway and take a balloon and stick the balloon on the inside of the opening to the water bottle and attach it, it would actually look like this. So here's the opening. Take a balloon, say a blue balloon, and put it on the inside here. And you take the lip that you normally blow through and put it on the outside here. And then you take another balloon and cut it so that it's just enough surface area to attach to the bottom here, and you're going to have to tape it to the bottom of the water bottle, this cut-off water bottle. If you were to grab the bottom balloon part and pull on it, that's like a diaphragm. When you pull on the bottom, it's going to take the amount of air in here, and it's going to reduce the pressure. Because you still have the same amount of air in there, but now you give it more space. And that pressure reduction is going to draw air here. You will see the balloon expand. That's how your lungs work. And that's why I mentioned in the previous slide about the importance of pleura and having that liquid layer. And if there was a leak in there, your lungs' ability to expand and contract is going to be significantly reduced and affected. You can do this at home. It's a nice demo of how the lungs work. The intercostal muscles are another part of the breathing mechanism. So when I'm doing more shallow breathing, I'm not making as much of a dramatic contraction and relaxation of my diaphragm. There's also all the muscles in between the ribs of my thoracic cage. The contraction of those particular intercostal muscles is going to elevate the ribs and the sternum so that my breastbone moves up and out and the ribs move up and out, and that's going to further increase the space that's inside the thoracic cage, and that reduces the pressure within here and draws air in. And the opposite happens when you exhale. Those intercostal muscles are relaxed, bring the rib cage back down, and cause air to leave the lungs. So diaphragmatic breathing and constant breathing, if I do take a really deep breath, you notice that there's much more of a diaphragm effort there. And more shallow breathing, kind of when you're just sitting there at night and thinking about breathing, you don't need to take deep breaths if you're just sitting there in a relaxed mode. You don't need to have that deep kind of breathing. It's called that costal breathing, because just moving your chest a little bit up and down is going to be enough to get air in and out. Forced breathing is another story. So forced breathing is even more significant than this deep diaphragmatic breathing. That could be due to stress, overexertion, hyperventilation to accompany this. So forced breathing is where your abdominal muscles and other accessory muscles are going to assist with getting air in and out. Abdominal muscles can, if they're acting in addition to the upper ones, they can force your diaphragm to do more dramatic contractions and relaxations. They're right next door to it. So forced breathing is going to be something that usually accompanies stress, some kind of problem in terms of the need to have that forced breathing, really dramatic breathing. Have you ever wondered what causes a hiccup? It has to do with the diaphragm. A hiccup is basically a very short inhalation. If this is the diaphragm, it's a spasm in the diaphragm. So normally when you breathe in, the diaphragm does. But hiccup is so what causes that spasm in the diaphragm? A lot of different things. Eating too fast and sucking too much air as you're eating quickly could irritate the diaphragm. Also, I've experienced this. You may have to laughing a lot could bring on hiccups. The theory behind that is really intense laughing is going to involve quick contractions and relaxations of your abdominal muscles, and since your abdominal muscles are right next door to where the diaphragm is, that could irritate the diaphragm and cause those spasms to occur from these hiccups. All right, when it comes to respiratory volumes, this describes the different levels of breathing in terms of how big of an inhalation are you taking, how big of an exhalation are you taking. If we start over here, this line here, that's just called tidal volume. It's kind of like your regular breathing when you're just at rest. And I know on the y-axis here it says milliliters per kilogram, but I think it's easy to think about just the total volume involved. For the average person, this is about half a liter, 500 milliliters. So I'm gonna move my pen along here and show you what's involved. So here we go. So I'm taking inhalations and exhalations that is very shallow here. Here's a big one. And so on. So there you saw what happened. I went way beyond that typical tidal volume inhalation and took in as much air as I could at that moment. And that's called inspiratory reserve volume. So your lungs can take a lot more air in than you normally do with this tidal volume, just 500 milliliters in, 500 milliliters out. And here I went another maybe close to a couple liters, and that's when you need it. So if you're taking a big breath because you're going to hold your breath, you're getting ready to do something, you're going to need to take a bigger breath there. And that's known as the inspiratory reserve volume, which is the amount of volume your lungs can go past that tidal volume. And then I exhaled so much, I even exhaled past that tidal volume level and tried to exhale as much as I possibly could out of my lungs. Below the tidal volume, they call this expiratory reserve volume. And it stops here instead of going all the way to zero because you don't want to let every last bit of air out of your lungs or your lungs collapse. If you take all the air out of your lungs, there'd be no air pressure or gas pressure, and upon the lungs just deflate. And a collapsed lung is not good for breathing. Specifically, what's called residual volume, it's, I think, a little less than a liter in the average person. So residual volume is the amount of air that tends to stay in your lungs. Now, if you get hit really hard, let's say in the abdominal area, that could cause someone to say, oh, they lost their breath, they got the wind knocked out of them, is another way for that to be expressed. That could cause some of that residual volume to be expelled, and the person can have trouble breathing. So it's good that residual volume is kept in your lungs so that your lungs don't collapse. Right here, this inspiratory reserve volume plus tidal volume, this should actually be phrased as inspiratory capacity. So this is your total volume for the amount of inhalation that you can take in terms of the amount of air. So inspiratory is like saying, maybe quality of inhaling. So inhalation, inspiration, same thing. It's all of this area below tidal volume, the amount of air that you can exhale below that, including the residual volume, that's called the functional residual capacity. So that's ERV plus RV. And then the total amount of air from the total max you can inhale to the total max you can typically exhale is called vital capacity. That's the range you have control over. So that's a lot. And of course, you don't want to get rid of this, but if you add together the vital capacity and residual volume, that's the total volume of air that you could possibly take in the total lung capacity. And of course, this is variable in terms of precise measurements. I mentioned 500 milliliters earlier for the tidal volume. In someone that's really petite, it'll be less. In someone that's really large and has really large lungs, it can be more. Partial pressures of gases is what actually gets gas in and out of the alveolar sacs in your lungs, and getting it into your lungs for that matter. The major atmospheric gases, if you look at the big four, nitrogen gas, oxygen gas, water vapor, and carbon dioxide. Nitrogen gas is about 78% of the atmosphere. Oxygen gas is close to 21%, and the rest is these two and other ones that make up 20% of the atmosphere, like argon, etc. So partial pressure determine how much each gas will flow into and out of liquid from the air. And it all comes down to diffusion. Yes, you are actively expanding the lungs and contracting them in terms of the muscles effect on expanding and contracting the lungs, but the movement of air in and out really comes down to diffusion. You're not using active transport or ATP to drive oxygen in and to drive CO2 out. It's diffusion, which is that passive natural process. So that's why it comes down to pressures. If the pressure is higher here than here, the gas is going to go that way. And that just comes down to gas laws. It's going to drive gas to where there's less pressure. And of course, altitude can have a dramatic effect on pressure. The reason why some people get short of breath when they go high up in altitude is because if you look at the atmospheric pressure and partial pressures of gases at sea level, there's a lot more oxygen in terms of the pressure and the amount of oxygen that's in the atmosphere at sea level. You go up, let's say, 2,000 meters, 4,000 meters, going up really high mountains. There's a lot less gas, specifically oxygen gas. So the partial pressure of oxygen at that altitude much less. So the amount of oxygen that is then going into the liquid layers of the alveoli is going to be less. So people are having to take more inhalations to accommodate to get the oxygen in there. And that can lead to, like I was just explaining, shortness of breath, lightheadedness. People are more likely to pass out from having less oxygen entering their lungs. So altitude definitely a player that makes sense in terms of partial pressures. Oxygen, the reason why it moves out of alveoli and out of the, once oxygen comes into the bottom part of the respiratory, it moves out of alveoli into your bloodstream, is because if you look at the amount of oxygen in the capillaries that are going up into the alveolar bundles, the pressure, partial pressure of oxygen is greater in the alveolar sac than it is in the capillary, and that's why oxygen goes in the capillary. Conversely, it's opposite when you look at CO2. If this is an alveolar bundle, and here's the capillary going right next to it, here's another capillary going right next to it, CO2 pressure is going to be lower in the alveolus than it is in the capillary. So in the capillary, CO2 pressure is greater because CO2 is that waste product you get from the cells doing aerobic respiration. You want it to go back to the lungs, so your capillaries are kicking it back into here. And because of the fact that the partial pressure of CO2 is greater in your capillary than it is in here, the CO2 is going to make its way from the capillaries into the alveolus, allowing you to exhale. And it's the opposite flow with oxygen because the partial pressure is flipped with that gas. If you look at this particular graph here, it shows you in the different parts of the atmosphere and in the body how the partial pressures work. Notice with nitrogen, it's almost the same throughout. In the atmosphere, the partial pressure of nitrogen is a little greater than within the body. It doesn't change much in the body. Nitrogen is such a major part of the gas that we inhale, and a major part of the gas that's found in the bloodstream. That's not going to change that much. But when you look at oxygen, look at the percentage in terms of the partial pressure of oxygen in the atmosphere and how it gradually gets lower. The partial pressure of oxygen can only drive it so far deep within the body. So it does get to our cells, but the relative amount of oxygen that's in the cells of our body compared to the amount that's in the atmosphere is significantly less. The alveolar gas, it's the gas that's actually in the alveoli. Here's the partial pressures in arterial blood, taking that blood to the body out of the heart. And then venous blood, this is the blood going back to the heart, and like I mentioned earlier, this is partial pressures within cells. And finally, some respiratory conditions and disorders. Asthma is chronic bronchoconstriction. So the bronchioles in the lungs, if you have problems expanding them, that can lead to asthma. And the thing is, asthma attacks happen when somebody who has that slightly more restricted bronchial set, they do physical exertion. Let's say they're playing a soccer game, playing a softball game, what have you. And the need to get more air into their body because their heart's beating faster and they do more of their muscles, that's when the asthma attack can happen. And it's not just because of physical exertion. Stress can bring on an asthma attack. So the treatment for asthma, because there currently is no cure, is bronchodilators. So the inhalers that people use when they have asthma or when they get an asthma attack, those inhalers, they chemically cause a dilation of the bronchioles to get more air into the respiratory tree and they get relief from that. One treatment for asthma that I've heard works for some people is somebody who lives in a very urban area where the air quality is poor. Maybe they live next to factories, they live next to where a lot of cars are with the exhaust coming out of the pipes. If they move to a more rural area, to the countryside, the air quality will look better, and that can actually have a positive effect on some people with asthma. Their symptoms are reduced oftentimes when they do that. Emphysema is a gradual deterioration of the alveolar bundles in the lungs. If those little sacs get damaged and there are more spaces in the lungs, the ability to adequately get air into your bloodstream with each breath is reduced. Emphysema happens because of smoking, because of intense smoke. Usually it's a trauma that's going to cause that or smoke. But over time, as a person gets older, you're more likely to experience symptoms of emphysema. So in elderly people, emphysema tends to gradually happen, at least minor symptoms, even if they never smoked. So that inevitable damage that happens over the years to lung tissue is just more common the older you get. Lung cancer is when you get the development of tumors in the lungs. So emphysema can lead to lung cancer if emphysema is bad enough. And lung cancer is, of course, more likely to happen if you are a smoker, but even people who never smoked a day in their life can get lung cancer. And lung cancer, like many cancers, has been able to spread to the parts of the body, especially because there's so much blood flow in the lungs and lymphatic tissue that you find all throughout the body. So the spreading of lung cancer to other organs, this is what's going to tend to kill a person. Laryngitis and bronchitis, those are irritations or infections of the larynx and the bronchioles. Laryngitis, an infection of the larynx, is very magnified down like this because your voice box, your vocal folds and vocal cords are in the larynx. So infection of that should definitely have an effect on your voice, or you can lose your voice entirely. And then bronchitis is an infection a little bit further down the respiratory tract, and that can usually be accompanied with coughing. The thing with sneezing and coughing is sneezing tends to be irritation in the upper respiratory tract, so getting dust or particles into the nasal region and the throat region is going to be, causing you to have that sneeze. And in case you didn't know, sneezes happen at over 100 miles per hour. Bronchitis, or getting deeper irritation, production of mucus, excessive production of mucus or irritation in the lower respiratory tract is going to cause coughing. That's your body's natural ability to try to get that stuff out. Cystic fibrosis is a genetic disorder. These are genetics and biology. It's autosomal recession. And cystic fibrosis is we have a problem with a certain kind of protein channel in your cells that's supposed to shuttle along an ion. If you're not able to do that, the accumulation of those ions, those charged atoms, tends to attract water because of osmosis. And cystic fibrosis leads to production of excess mucus or collection of excess mucus in organs like the pancreas and the lungs. So cystic fibrosis does affect the lungs. It's one of the main places that you get the negative consequences of cystic fibrosis. There is no cure, but there are treatments for this disease. Decompression sickness, also called BENS, tends to happen because of dramatic altitude changes, or, more commonly, if a scuba diver has to go really deep and they come up way too quickly to the surface, because they were down low and they had a highly compressed oxygen tank getting oxygen to the lungs, if they don't go up gradually and adjust the pressure of their bodies to reactivate, going up easy past the surface is going to cause a dramatic accumulation of nitrogen gas in parts of the bloodstream, and it can kill a person. It can be very painful in terms of accumulation of nitrogen gas in the joints. So if you do have somebody who gets aggressive or the BENS, you want to take them to a hospital nearby. We're going to have a hyperbaric chamber, and that can cure the BENS. Some people, it just happens to quickly dramatically. So it can result in death. Tuberculosis is a bacterial infection of the lungs caused by bacterial tuberculosis. That you don't see as much in first world countries and industrialized nations anymore, but it does happen occasionally. And this bacteria gets into the lungs and goes through what Harry goes into the bacteria divides and moves around the lungs. You can develop a thing called tubercules, these little sets of bacteria, and as they grow, as these bacterial colonies continue to grow, as tubercules, they can break and cause bleeding, cause massive lung bleeding, and that's why they're coughing up with blood. And so the tuberculosis is usually called permanent death. So if you don't get treated with antibiotics early on, it can lead to death. There's a test they do where they take a little section of your form, and it's a little bump, and you go back a couple days later, and the bump's gone away. That means that antibodies to tuberculosis you've never been exposed to, means you're not sick with it. If that bump does not go away, it means you've been exposed to tuberculosis, that kind of bacteria. Because if you've been exposed to it and it's gone into your body, it doesn't mean you have the infection. To see if they actually have the tuberculosis colonies in their lungs, they do a chest x-ray, and that chest x-ray will reveal whether or not you have a little tuberculosis, little fats connecting itself with how they connect to other parts, treatment for other parts of the brain, and then there's something to do with it. So if you have the child talk to the physician about how to maximize not accidents. Pneumonia is a bacterial infection that causes production of lots of mucus at the base of the lungs where you have those bronchioles and alveolar bubbles. And pneumonia can be fatal. It can be cured, but it doesn't lead to death with some people. It's going to tend to kill somebody who is much older, who has been a chronic smoker. Like I mentioned earlier in the lesson, people who smoke a lot tend to damage the cilia that are connected to the excess mucus that you don't surround your own blood vessels in there. Pneumonia has to do with basically filling in the fluids, but it can be cured. Pneumothorax, like I mentioned earlier, is a leakage of air into the space between. It's like more of a magnet. Carbon monoxide will attach to heme much more efficiently than oxygen is. So if there is a carbon monoxide leak in someone's house, this gassy in one of their gas supply systems, oven, whatever, if all the windows are closed and there's no way for the air to leak, the carbon monoxide can gradually kill a person. Carbon monoxide is fluorless, tasteless, smellless. Sometimes carbon monoxide is capability of a chemical that does have smell, so if it ever happens, especially, they recommend that they're putting a carbon monoxide detector in their house. It's not very expensive, just plug it into one of your outlets, and there is carbon monoxide in the air. The alarm will go off, and that means get out of your house immediately, call 911. So if you're going to use a carbon monoxide detector, it can save lives. This is why welcome back to educator.com. This is the lesson on the heart. When we look at the anatomy of the heart, there are several layers that we can consider. The pericardium is technically not the heart itself, but what you can see here is it's kind of cut away. You see this pericardium cut away. It's this connective tissue sac that in a person's thoracic cavity, if you were to open up, you would see almost like saran wrap or opaque than that around the entire beating heart. And that particular connective tissue sac is not only protecting the heart and giving it some extra layer cushioning, but in between the pericardium and the surface of the heart itself is fluid, and that's providing lubrication. So think of it as like, the engine of your car without oil and the engine, all those moving parts that are metal on metal, it wouldn't work quite as well. It needs too much friction. So having that fluid in between the inside of the pericardium and the surface of the heart is very important. The epicardium, remember, epi means superficial. We're talking about where it's on the outside. The epicardium is the actual surface of the heart, very thin in terms of the rest of the layers. When you go deeper, the myocardium, the thickest layer of the heart by far, is all that muscle, that cardiac muscle, very thick. If you've ever cut into sheep heart or cow hearts, they're a lot bigger. If you're dissection lab, the myocardium is very thick. And it's important. You want it to be strong. You want it to last a lifetime and do the job of making blood. The endocardium is that inner layer, the deepest layer of the heart tissue. It's very smooth, like a slippery slide. Very smooth, they have epithelium, and you can call it endothelium because it's very deep. That's what the blood itself is slippery sliding along. And you want it to be smooth. If the endocardium is rough, it will damage or rupture too many red blood cells. So you want it to be nice and smooth for this process to work properly. The atrium and ventricles are the main chambers. You can see here, this is the right atrium. From this view, it's hard to see the left atrium. It is over here, the oracle of the left atrium, is just the corner of it. If you turn the heart side, you'll be able to see the left atrium a lot better. But those are the superior, smaller chambers of the heart. If we go deeper, you would see the right and left larger chambers. You can say there's a right and left. So keep in mind that this is from the point of view of the person whose heart's long. From my point of view, if you look at the heart, my left ventricle is on that side, your right. But we got to keep in mind it's from the point of view of the subject. So that's why even though the left side is drawing, this is called the right atrium. The right ventricle would be in here. So keep that in mind. If you're looking from the posterior side, you're looking from behind, then your left would be the same left as the subject. The coronary artery is a general term for the